I'd like to do the following integral. Integral of square root of 1 minus x squared in two ways. One, using this new topic that we're going to talk about called trigonometric substitution. Another method, which I want to do first, is using geometry. What I'm going to do is I'm going to consider a related definite integral where the upper limit of integration is a variable. This also has the benefit of re-emphasizing the truth of the second fundamental theorem of calculus from chapter 6. This function of x by the second FTC in chapter 6 is an antiderivative of this function we're integrating right here. Right? This indefinite integral symbol means find an antiderivative. FTC, that's by definition. The FTC part 2 theorem, fundamental theorem of calculus that you have to prove, would say such a function like this has a derivative equal to this function right there. It does. The variable for this function's x is in the upper limit of the integral. Writing it as a definite integral allows me to solve this one, or to think of solving it, by finding an area under a graph. It's going to be the graph of this function, 1 minus t squared, as a function of t. What does the graph of that look like? Some of you may know just by looking at it, its graph is the upper half of the unit circle. Maybe you can see that, maybe you can't. This is y equals square root of 1 minus t squared. Y, well, the equation of the unit circle itself in a ty plane would be t squared plus y squared equals 1 squared. If you solve for y by subtracting t squared from both sides and then taking a square root, taking the positive square root to get the upper half of the unit circle, you would get this exact same function. Where's x in this picture? It doesn't matter, though it's convenient to make it be in the first quadrant over here, maybe right there. Let's say that's x. I can pick it to be anywhere, though. T is kind of thought of as the label for the axis. X is a particular number on that axis, though I could change where it is. I could vary it. I can think of it as a variable. But for any fixed x, this integral represents an area. It's the area under the curve between 0 and x. Because this example is with a unit circle, the area can be figured out with geometry and trigonometry. You can split this region up into two regions, one of which is a triangle, a right triangle, in fact, and one of which is a wedge or sector of a circle, or if I prefer saying piece of pie, or pizza pie is a piece of pizza. Okay? There's that. We know the formula for the area of a triangle. Area of this triangle is 1/2 base times height. What's the base? The base is x. If this number on the x-axis is x, on the t-axis is x, then this distance is also x, because I'm going from 0 to that number. So the base is x. What's the height? It'd be the length of this blue line here. It would be this thing. Replace t with x. That's the area of the triangle. What about the area of the piece of pie? Maybe you don't know the formula for the area of a sector of a circle. Can we rederive it? Yeah. If you assume the angle here, label this angle theta. If you assume that's measured in radians, Turns out the area of this is 1/2 theta. Why? I'm not going to prove it, but here's an argument for why this should be reasonable. Think about the entire unit circle, centered at the origin with a radius of 1. What's its area? Pi r squared. But r is 1. Pi times 1 squared. Pi. The area of the unit circle is pi. What's an angle that goes all the way around the unit circle in radians? 2 pi. 1/2 times 2 pi is pi, the area of the circle. What if it were half the unit circle? The angle would be pi in radians. 1/2 pi is that pi over 2 that's the area of half the unit circle. 1/2 times theta, where theta is in radians. And it works with any other angle in radians as well. So I guess this integral being an area, the area under the curve must be the sum of these two things. This is a function of x, this integral. That already depends on x, but this doesn't. It does depend on x, though. It's a function of x. I can figure it out. Geometry. 10th grade geometry. You've got two parallel lines here and a line crossing them. What is it? Alternate interior angles are congruent. You remember that? This angle's theta. This angle's also theta in that right triangle there. So we have a right triangle. I'll redraw it here. This side is x. This side is 1. This angle's theta. So katoa, sine of theta is going to be opposite over hypotenuse, just x itself. Cosine theta is adjacent over hypotenuse. The adjacent side is, well, think about the function. That's square root of 1 minus x squared. Adjacent over hypotenuse. And if we wanted to figure out tangent theta, we could do that too. TOA, opposite over adjacent. Now, any one of these equations could be solved for theta by using inverse trig functions. But the simplest one to do it with is this one. So do it with the simplest. Theta, will be inverse sine of x. You could also write arc sine of x. Either way is okay. They are both the same function. I think arc sine is the older notation. Inverse sine is the newer notation. If my math history is correct, which I think it is. That's theta. So plug it in there for the area of that sector. Multiply it by 1/2. In other words, combine these things to say this integral equals 1/2 inverse sine x from this plus 1/2 x square root of 1 minus x squared plus c, no, not plus c, excuse me. This is really a definite integral. If I think of x as a definite number, there should not be a plus c. This allows me, though, to figure out the indefinite integral. That was my original problem. It's the exact same answer, but with an indefinite integral, you do need to put the plus c there. The indefinite integral really represents infinitely many functions, whereas this definite integral represents just one function. If I picked a different lower limit of integration instead of 0, maybe I picked -1, I would get a different answer. It would be a different antiderivative, a different c, so to speak. These two match when c is 0. If I pick -1 there, actually, since the function value at -1 would be 0, I'd have to add pi over 4, I think, to this, because the area of this part of the circle would be pi over 4. Oh boy, is this right? We better check it. Did you write the answer down? We're about to differentiate it here during one of my long arrows here, d dx. I'm about to differentiate that. You got it written down? Doesn't look like it's going to be so simple. You might be doubtful that it's going to work. Derivative of inverse sine is a memorized derivative. 1 over square root of 1 minus x squared. That's at least somewhat promising. We got a 1/2 as well. 1/2 times 1 over square root of 1 minus x squared. Got to differentiate this with the product rule. It's a product of two functions, a left and a right function. I have to do that, the product rule, and also the chain rule with the derivative of the right. Square root of 1 minus x squared is 1 minus x squared to the 1/2 power. I need the chain rule again. Left, d right, 1/2, 1 minus x squared to the -1/2. Chain rule gives me an extra -2x. Plus right d left, the derivative of 1/2 x is 1/2. There's right d left, and then the derivative of c is 0. Doesn't look like my integrand, does it? Take a breath. It is, that's right. You just have to simplify it to see. 1 factor of 2 will cancel. This fraction has a denominator equal to 2 times the square root. So does this one, actually. You say, hey, that's not a fraction. Well, it is. Well, the 1/2's a fraction, but also 1 minus x squared to the -1/2 is the same as 1 over square root of 1 minus x squared. It's the same denominator, 2 times square root of 1 minus x squared. This one's not a fraction, but we can make it into one. Let's see here. By multiplying by disguised form of 1, I already got a 2 in the bottom there, so the disguised form of 1 I need is the square root of 1 minus x squared divided by the square root of 1 minus x squared. And on the top, that's going to mean the square root goes away. Square root of 1 minus x squared times itself. The square root goes away. And on the bottom, I have that common denominator. It's simplifying. In fact, it's simplifying ultimately pretty nicely. The 2's cancel. And then this does equal the original function because I have a number divided by its square root. When the number is positive, at least, that is the square root of the number. Why? Because, well, you can think of it in terms of exponents if you like, and subtract the exponents like this to get that. Or you could think of a as square root of a squared. Let's see that. So check, it worked. Amazing. We're not done though. Let's do the exact same integral again. But now let's use trig substitution, which is this new technique. And trig substitution, yes, does not show up on the gateway. It's a harder, trickier method. We don't want to put such hard problems on the gateway, but they do show up on homework. They could show up on exam 1, maybe with some help. When your integral, your integrand that you are integrating, involves a square root or maybe something to the 3/2 power or something like that of something squared plus or minus something else squared, that's a big hint to use trig substitution. If it's a number squared plus or minus a variable squared, that's the most common thing. When it's minus sign, use the substitution x equals sine theta, We call it a trig substitution because that's a trigonometric function. Notice this is a little different than we did with W substitutions. We usually let W equal something involving X. Here we're letting X equal something involving the new variable, theta in this case. So it's a little different, but these are equivalent. This is equivalent to theta being inverse sine, at least for certain values of theta. But we don't worry about domains too much here. We've got to find dx. If x is sine theta, then dx is cos theta d theta. So using this substitution, you get the integral of square root of 1 minus x gets replaced by sine, dx gets replaced by cos theta d theta. Then, this shouldn't be surprising by now. We use the fact that 1 minus sine squared is cos squared theta. Technically speaking, the square root of cos squared theta is the absolute value of cos theta, technically speaking. But if we assume, hoping this assumption is okay, that cosine of theta is greater than or equal to 0, then we can get rid of the absolute value signs. So let's go ahead and make that assumption. You might wonder, is that valid to do that? And well, it's a situation where the ends justify the means. You get the right answer. So don't worry about it. I can get rid of those absolute value signs, then cos theta times itself is cos squared theta. And hey, we did that integral on Wednesday. Right? There are two ways of doing that integral. One with integration by parts and solving for the integral. And the other was with a trig identity. I highly recommend the trig identity method. Cos squared theta is 1/2 plus 1/2 cos 2 theta. Giving us 1/2 plus 1/4, 1/2 theta, excuse me, plus 1/4 sine 2 theta plus c. The 1/2 theta part looks good if you think about it, because theta is inverse sine, so this is 1/2 times inverse sine, just like we got with the other method. So that part looks good, but what about that part? More identities. Use that double angle formula that we did use on Wednesday as well. Sine 2 theta is 2 sine theta cos theta. Remember, theta is inverse sine of x. So sine theta is x. X is assumed to be between -1 and 1. So we can plug in the inverse sine function, get an angle technically between -pi/2 and +pi/2. Take its sine, we'll get the original x back. Cos theta is cosine of inverse sine of x. You can either draw a right triangle, help you figure out what this is, where one of the angles is labeled inverse sine of x, or you can use the Pythagorean identity, taking the positive square root. After all, we're assuming cosine theta is positive anyway. We would get this. And that simplifies to square root of 1 minus x squared. That's looking good too. We're almost done. Combine all these things. Theta is inverse sine of x. Then we get the 2 and the 1/4 cancel to give a 1/2 x square root of 1 minus x squared plus c, the exact same answer we got before. How about that?